But half cells, funnily enough, two half cells combine to form one electrochemical cell because they're a half cell. Each half cell contains an element in two oxidation states and an electrode that conducts electricity. Sometimes one of the elements, the element in one of its oxidation states can be its own electrode, and that's absolutely fine. So metals, solid metals that also become ionic or aqueous metals, sorry, my brain went funny then. Solid metals can often be their own electrode because they are a solid, they're metal, so they can be an electrode that can conduct electricity and provide a surface for the reaction between the aqueous substance and the solid metal itself. Obviously, and we'll come to it again later, if one of the oxidation states is not solid and or is not just a normal metal, then we will need to provide an electrode. And we'll come to that again in a second. In each half cell, both reduction and oxidation can occur, setting up an equilibrium. Which half cell does what in... So I think that's written slightly funnily. It should be in the electrochemical cell, both reduction and oxidation occur. One half cell is oxidation, one half cell is reduction, is what it's trying to say. Which half cell does what in the cell depends on their standard... where am I going to write that? No, sorry. Standard, there we go. Standard, crikey. Standard electrode reduction, and I'm going to put reduction in brackets because this is the bit where I'm fussy. I like to call them reduction potentials because that's what it is. They're not often taught like that. They're often just taught as standard electrode potentials. So I'm going to use the term standard electrode reduction potentials, or just reduction potentials. Potentials. E thingy with the standard symbol again. It's the same symbol. We're just calling it an electrode. Standard electrode reduction potential. The reason that I like to call them a reduction potential is because I think it helps us to understand what's happening and when and why reactions can and can't happen. If we just remind ourselves of oil rig, we cover it at GCSE, we still use it at A level, it's still applicable. Oil rig is oxidation, oh my goodness, my spelling. Oxidation is loss, reduction is gain of electrons. It's the same as it was at GCSE. Oil rig is applicable for electrons, the exchange of electrons. So oxidation is the loss of electrons, reduction is gain. And this red box, I personally have never learnt what an oxidizing agent does or can do, or a reducing agent does or can do, because I work it out every time. So you can learn it off by heart if you want, or you can understand it and then work it out. So oxidizing agent, if it's an oxidizing agent, then it is going to be oxidizing something. So if it's oxidizing something, then oxidation is loss, so it's causing something to lose electrons. So the way it can do that is by it gaining those electrons, forcing something to lose electrons. So it is gaining electrons, so it is reduced. Reduction is gain of electrons. I know it's a long way around and you might prefer to just memorize it, but by doing that, I've leaved space in my brain to memorize something else. And similar for reducing agent. A reducing agent is going to reduce something else. It reduces something else. It causes something else to gain electrons by losing electrons and giving that thing electrons. So it itself is oxidized. Okay, so let's have a look then at a full cell which includes zinc and copper half cells. So this is a kind of an example. Obviously, you guys wouldn't use color, but this is an example of a diagram you may be asked to draw for a cell. And you do need to be able to label it correctly. So here we've got, what do we say, zinc and copper. So we haven't been given information either way, but I will tell you now, copper is reduction. The copper half cell undergoes reduction, zinc undergoes oxidation. So which way around do you write it? Which usually, not all the time, because the standard hydrogen electrode makes things a little bit more awkward, but which way around do we usually write things? And I can promise you there is a way. We write reduction on the right when we're doing standard notation, when we're doing diagrams, when we're, I'm sure there's not somewhere else. Anyway, reduction on the right. So this right-hand side is reduction, or shows reduction. That is the reduction half cell. And so the left-hand side must be oxidation. Reduction on the right. Oh my goodness, my handwriting. Reduction on the right. That's redden, reduction on the right. What did I say? Copper is reduction. So this is copper. So what's going to be what? Where is copper going to exist? That must be copper solid. That's my electrode. Actually, let's call it a copper electrode. That makes more sense. Electrode. And therefore, I'm going to have copper in solution, an aqueous solution of copper. Which ion is it likely to be? It's most likely to be copper 2+. Solution. And therefore, on the right, this must be my zinc electrode. Oops, he's treading on something. Zinc electrode. And this must be my zinc solution. Oh, I didn't give it a charge, sorry. And again, it would be Zn2+, so zinc 2+ solution. What else can I label on this diagram? You don't need to label beakers or wires, but what's this thing likely to be, or what does it look like it could be? It's going to be a voltmeter. Useful for measuring the electromotive force, the EMF of the cell as a whole. And then this thing in the middle is what? That is our salt bridge. Make sure I spelled that right. What else did I want to include? Oh, I'll just put Zn2+ aqueous there, just to make it absolutely clear. And copper 2+ aqueous. So that is a copper solution. Oh, equations, that's a good idea. So what equations are going to happen? And I'm going to write them as the reduction equation, because your reduction potentials are given as the reduction equation. So reduction, oil rig, reduction is gain of electrons. So I can show my zinc, Zn2+, gaining 2 electrons in a reversible reaction to form Zn solid. And my copper, I can use copper 2+ aqueous, gaining 2 electrons to become copper solid. That is reduction in both cases, but we have already said reduction goes on the right, so that will be traveling, the equilibrium will be pushed way over to the right on that equation. So we'll be mainly going in the forwards direction. But with the zinc equation, that is going to be pushed in the backwards direction. So you'll actually be getting oxidation happening. And that is, we can label those as oxidation therefore and reduction. Was there anything else I wanted to say? Can't remember. Let's add that down there. So note the more negative electrode potential is drawn on the left, or I would think about it in terms of reduction. So reduction is on the right. So the more positive reduction potential, the more likely thing to be reduced. The more positive reduction potential goes on the right. Reduction on the right. RR. Bit easier to remember, I think. And again, I would personally think about it in terms of reduction, because that's what our reduction potentials are given as reduction. Okay, what else? Oh, and I'll just put, there should be a usually in there, because of course within the standard hydrogen electrode, when we're measuring electrochemical, we're measuring the electrode potential of specific half cells. The standard hydrogen electrode is always on the left, so sometimes you won't have the more negative electrode potential on the left. Sometimes it will be on the right. So usually we draw reduction on the right, apart from maybe with the standard hydrogen electrode. Okay.